So for context, I've tried for many years to get Thore up here. I've been a long time admirer of his work, and as I'm sure many of you are as well. I spent many years at MSR, and then most famously at DeepMind, running the multi-agent team. If you watched the AlphaGo documentary, I think you are one of the star cast members. I certainly remember you in a few of the frames. And then since then, he's gone into the domain of biology, which, as you probably know by now, is one of my favorite domains. He runs the computational AI team across a really inspiring company called Altos Labs. And I hope we'll dig into a few of these sort of steps in his career. So to start, I thought we'd go back down memory lane. I think one of the main things I want to kind of impress on people is just AI progress today is really exciting, but some of you have been working on this for decades. And so if you could take us back perhaps to the days of AlphaGo at DeepMind, and kind of unpack a few of the breakthroughs and what they felt like. Was it apparent in the moment that you guys had achieved something big? Are there some similarities with the feelings of these breakthrough moments as we're going through some of them today?
Yeah, great. Thanks for the invitation and the nice introduction. So it's nice to go down memory lane. It's been 8 years now since the AlphaGo match in Seoul. And it was really quite a remarkable research adventure. One thing I'd like to start out with is it was really quite surprising how an obscure board game like the game of Go that is hardly known in the West could gain such prominence suddenly through an AI project. The people who came together in the project was a very diverse set of people. And one thing I can only emphasize is that I just had the greatest team members to work with on this challenge. Dave Silver, who is of course the expert in reinforcement learning. Ajia Huang, who was a very strong Go player himself and knew a lot about tree search. Julian Schrittwieser, who is a kick-ass developer who can zoom in to the smallest detail and zoom out to the system design. So some amazing people. So and that is one of the elements that we're talking about, that there is a team of people who have each their diverse expertise, also have a tremendous respect for one another, and somehow are aligned on a mission, even if it's such a strange mission as taking a 3,000-year-old board game and trying to make a computer play it as well as possible. And what maybe explains this idea that why Go turned out to be such a turning point in a way for the field is this idea that we can take games and treat them as a microcosm of the world. And games, of course, have been designed to be microcosms of the world. That's why they're fun, right? It's in the game of Go, it's the idea that there's space, there's time, because we take turns making the moves. There's some form of resource. There's territory that you want to surround. So there are a lot of ideas that play, in some sense, a role in the real world. And what I find fascinating is that, this gained a lot of prominence, certainly a great adventure to go to Seoul and play with Isadol and win that match. But also what we saw in the project is that I think a lot of what will play out for the real world in AI was in some sense preconceived in the AlphaGo project. Because one element is you always deal with humans. There was a human community of Go players, and they cared for this game. They had long-standing traditions, and we had great respect for that. But now you bring in technology, and of course it disrupts that community to some degree. Then we had this setting of human, in some sense, versus AI in the match, which is an adversarial setting. But really what we want to achieve, of course, is that our AI systems are helpful in collaboration with humans. And then we also saw some effects that I think we will see mirrored in the development of AI, whereas the original version of AlphaGo actually played fairly human-like. Go, you would recognize patterns. The system either learned them from human training data or discovered similar patterns. When we looked at this later, when we had developed AlphaZero, which was much stronger and didn't depend on any human patterns, it played in a way that was almost uninterpretable for a human. You know, suddenly it made moves across the board and you were thinking, what is it doing? What's happening? And only 20, 30, 40 moves later would everything come together and show you how superior the computer was at playing this game. And this is also a pattern that I could imagine might emerge in other applications, where at some point maybe we don't quite understand the actions of the AI anymore because they are beyond our planning horizon. Yeah. And I think it's great to have these little models like games to at least qualitatively understand what that feels like when suddenly you are confronted with a superhuman AI system.
Yeah. You touched on so many important points there. Perhaps one that I think is topical today is this idea of recursive self-improvement and agents working with agents or with humans. There's documented evidence that Go players become better as they're working with these systems. Do you have a sense of whether this idea of recursive self-improvement towards AGI is hyped or underhyped based on what you saw over the last 10 years and perhaps some of the artifacts we're seeing today?
Yeah, I think that's a very interesting question. I think this must be coming. And of course, even the idea of agentic AI, when you're a reinforcement learning researcher and you hear people now being excited about agentic AI, and you think, yeah, right, we thought about this in the past. You know, these are known ideas. You have an agent, and maybe you have better ways of forming initial plans now, and this agent has more world knowledge through large language models. But it doesn't change the fact that these agents eventually want to achieve goals, or we want them to achieve goals. And that means they need to interact with the environment, collect information. They need to learn from how they interact with the environment. There's going to be some reward function. We want to probably maximize long-term reward rather than short-term reward. And that then puts us into the framework of reinforcement learning. Yep. And which has been studied for a long time. And there's almost this irony that DeepMind, of course, was very focused on reinforcement learning, but then it turned out that drawing on the, if you like, crystallized proceeds of intelligence that have been produced and that are available on the internet, to draw on that first and train large models to extract knowledge out of that turned out to be the faster short-term solution for making progress. But I don't think that means that we don't need to eventually also look at the good old ideas of planning and of recursively self-improving systems.
So clearly over the years, reinforcement learning actually had a huge impact, or deep learning had a big impact on multi-agent RL. Now all we talk about is Gen AI. Do you see any particular impact of generative models within this multi-agent framework? Like, are the two sort of like positively aligned? Can we gain more by working with both, or are they separate fields?
Yeah, no, I think they are aligned in two interesting ways. One is architecturally. I think it will be very productive to have multiple expert large language models that interact with one another. Many of you will have seen this work out of Stanford, where there was a community of LLMs that where each LLM was kind of primed to be a particular character, and they then interact, and there's a birthday party being organized and things like that. But also similarly, people have designed company-like structures where, you know, you want to do some web development, and then you have a request coming in, and then there's maybe a project manager who distributes or the workload to different LLMs, and then there's a coder and a tester and so on. And so in that way, I think multi-agent architectures will be very important to move the field forward. They have nice modular structure, and you can draw and reuse components that you have. But the other aspect is that multi-agency also comes into this if we want it or not, because just imagine a world in which we now all have a personal assistant who acts on our behalf. And these agents now come together at marketplaces, buyers and sellers, or in social network settings, or in dating settings, God forbid, and start acting on our behalf. Then, you know, this isn't an architectural choice. This is just what the world is like, because behind each of these agents, there will be a principal, you know, the person who this agent serves, in some sense, who it represents. And these agents are now, their interactions now mediated through these artificial agents. And now you're in a multi-agent setting, and ideas of game theory apply, and all the richness that we know from human interactions will be there. Conflict, cooperation, betrayal, lying, you know, everything really. And so there's really these two things. We can embrace it for architectures, but also we're just in the middle of it if more than one party decides to use LLMs to represent them.
Yeah, and given how many, I guess, themes and topics we've talked about are important towards building more and more capable systems, are there any learnings from the organizations that you were in that could teach us about how to best structure teams, how to think about pulling these different strands together in the same company when you don't have a ton of resources, perhaps, or maybe if you do have a ton of resources, in order to actually drive progress? I think, you know, DeepMind is quite famous for being very effective at this compared to other organizations.
Yeah, it's very interesting. In some sense, at DeepMind, there was this guiding mission, solve intelligence, a bit like Bell Labs' mission, connect the world, a very general mission that allowed people to find their own interpretations of what that means, and then come together in projects to make progress towards it. One thing from the AlphaGo project that I would like to emphasize is the unpredictability of these things. You can plan certain things and try to make progress, but nobody could have expected that suddenly the game of Go raises to this level of prominence. It was really just because the right kinds of people with that common passion of making this thing work came together at the right point in time. And I think knowledge work is always like this. One of my favorite books is The Beginning of Infinity by David Deutsch. And he points out that the development of knowledge is really such that whatever problem we have, more knowledge is the answer to that. He calls that the principle of optimism. But a follow-on statement is that whenever we solve a problem and with some kind of solution, knowledge-based solution we come up with, that creates new problems that we then need to solve. And that creates this infinite growth of knowledge. And one thing that is the case is before that new frontier of knowledge has been developed, there's no way of looking behind that horizon. And that's why we will always be surprised. We can, you know, guess what might happen, but there's no way to reliably predict this, because if we were able to predict it precisely, then it would have already happened.
Yeah. So why did you not kill the AlphaGo project before you had the good results? How did you know that you could keep pushing and you would get a result?
Yeah, well, part of it is great leadership, for example, by Demis, who believed in this domain and believed in the team, and then helped us to structure this process so that we also had something to work towards. You wouldn't believe it, the power of public humiliation for motivating people, right? You know, when we had arranged the match against Isidol, you know, energy was very high to achieve this. And of course, we didn't know how it would end. We had this test match against Fan Hui, who already is a very strong professional player, but still quite a bit away from Isidol. And so you come into this match situation and you don't know where you stand. There just was no way to determine this a priori. And so the only thing you can do is be humble, right? And say, you know, we don't know, and hope for the best. Yeah. And then, of course, when Isidol, in fact, won one game, panic was high because, what does it mean? Has he cracked it? Could he win again? So very, very exciting times.
And speaking of humbling problems, I think many friends who've moved from AI into biology describe that as a pretty humbling domain because God knows how much of biological systems we don't yet understand. I'd be interested in your motivating kind of reason for going into biology, and perhaps what you were kind of least surprised in making that transition, or most surprised about.
Yeah, so I think biology is the hardest game in town, to be honest. I mean, I've never seen so much complexity in one place matched by so relatively little data, sparse data across the domain. So one way I like to think about it is biology is this multi-scale phenomenon. It starts with molecular interactions, then we have subcellular structures, we have cells, we have tissues, we have organs, organ systems, we have organisms, and arguably we have societies on top of that as a stack, but that's incomplete. I mean, there's many more layers in between. And in drug discovery, we're really trying to do something that should be completely impossible. Namely, if you now imagine this stack, we're trying to find an intervention here at the molecular level that then percolates through these layers of abstraction and scale to have a predictable and beneficial effect at the organismal level. Just imagine the complexity. So in principle, you'd think now we probably have to model through 10 orders of magnitude of scale and of time in order to ever be able to predict what a given intervention would do. But we don't just want to do that. We want to control. So we need to find for a given biological outcome that we're looking for the right intervention, which is a control problem. And so I am humbled. Yes, I am humbled. And I think there are domains where, and we've just seen this in the previous talk, where there is a lot of data, and those are great starting points. But the further you go up in this scale hierarchy, the sparser the data gets, and also the more critical things become, because now you're dealing with humans whose well-being is at play. And so solving that problem to me seems one of the hardest, but also, of course, most valuable problems we can tackle.
Yeah, and you touched on drug discovery. Probably the majority of companies are working on oncology or neurology or weight loss or sort of these very big kind of disease categories. Not that many people are talking about or working on cellular rejuvenation or regenerative medicine, which was very exciting after the Nobel Prize for cellular reprogramming was issued in 2008 or something, I believe. Can you tell us a bit about what you guys are working on at Altos, or what the mission is, and if you're successful, what does the world look like?
Yeah, with pleasure. So maybe a good starting point is we think a bit about a piece of data that is pretty intuitive. As we age, the probability of diseases happening, disease incidence, goes up exponentially for some of the biggest diseases, some of the biggest killers: cardiovascular disease, cancer, diabetes, dementia. These curves are really exponential. And it's roughly at my age, actually, that it goes up. So maybe not a coincidence that I'm caring about this problem more now than I used to.
Many people remark that you look a lot younger since you joined Altos. So.
And so it looks like that there is this common factor that increases risk, which is age. But what is age? And we try to frame this as some form of resilience or buffer capacity that an organism has when it's exposed to various stressors, disease stressors. That would seem to explain this type of data. And so, whereas traditional medicine looks at all the different diseases that exist and tries to understand the pathophysiology behind the diseases, what goes wrong physiologically when this disease occurs, then try to understand the causes of that, for example, genetic protein interactions, and then try to target for that particular disease. But the data that we have suggests an alternative, which is maybe we can work on the resilience side of cells and tissues. Maybe we can make them more useful, more resilient, more adaptive in some sense, and thereby create therapies for a number of these diseases at the same time, based on this same core idea of making the cells more resilient. And you know, this sounds a bit like science fiction. You know, if we didn't know anything, that would really sound like maybe too good to be true. But there is this amazing set of results in reprogramming and partial reprogramming, where Yamanaka and later others have shown that if you take a somatic differentiated cell, a skin cell or a liver cell, and you overexpress 4 particular transcription factors known as the Yamanaka factors in this cell, then this cell walks back the developmental path towards becoming a pluripotent stem cell. And the pluripotent stem cell is a cell from which any other type of cell type can develop. And whereas that is in itself pretty spectacular, I think, it also turns out that in this process, the cell is rejuvenated when it goes on this journey back in development. And it turns out that we can tap into that and do something that's called partial reprogramming, where only for a period of time we overexpress these Yamanaka factors. The cell goes a little bit on the journey back towards pluripotency, but remains in the basin of attraction, as it were, of its cell type. And when we then stop early enough the overexpression of the factors, it finds its cell identity again. So it retains its cell identity, and it is rejuvenated by a few years. And then you can do it again. So at least that's what it looks like. We have to be careful with the term rejuvenated, but you know, we look at various biomarkers, and also this has been shown to work on mouse models of aging. And so there really is an intervention that could hold the potential to do this for us. And the second ingredient that I find important, and remember my background is in reinforcement learning, I not only like to have an action that I can take, like this one, I also like to have a readout about, you know, how successful that is, a reward function, if you like. And that's where so-called epigenetic clocks come in. My colleague Steve Horvath at Altos Labs, he has discovered that you can read out the methylation patterns along DNA. They're little chemical markers along the DNA sequence, an epigenetic signal. And computer scientists can think of it as a binary vector almost. Either it's there or not along the DNA. You can do a regression of this towards the age of the organism. And it turns out that you can train a predictor that takes a bit of tissue and predicts the age of the organism. And now that in itself is pretty cool. Okay, we can see from the DNA epigenetics how old an organism is, but it turns out that this is also modulated by disease. So if people get less well, then this aging clock accelerates. Whereas if they do a more workout and, you know, various interventions that are possible, then this aging clock slows down. And so this might be the beginning of developing biomarkers that actually characterize something that you might call a biological age. And that would be the signal that you would want to optimize if you think about rejuvenation or strengthening the resilience of cells.
And what gives you confidence that you're making progress on this problem, given it's such uncharted territory? And to what degree does, you know, do modern methods in machine learning actually help you?
Yeah, so in some sense, one way to think of the problem is as a big search problem. You know, we want to find, for example, transcription factor combinations that have beneficial effects on the cell. And that is, you know, not unlike other machine learning problems that we're familiar with. For example, in AlphaGo, you know, that we had to find or navigate a combinatorial structure, namely the game tree, to find optimal sequences of moves. And here we now have a combinatorial structure, namely, say, subsets of transcription factors. And we want to find subsets that have a rejuvenating effect. And so how do we describe that? Well, first we need to learn in some measurement or output space what it actually means for a cell to be healthy, to be resilient, maybe to be younger. And so, you can take, for example, gene expression as a signal, and you can try to characterize what it means to be resilient or young in that space. And then you can think about a predictor that tells you for a given set of transcription factors how a cell would react, how its gene expression would change if you knock down or overexpress those transcription factors. And now you can build a little bit of a discovery engine to identify, say, combinations of transcription factors that would have the desired effect. But that's just an example. It could be small molecules, it could be other interventions that you can look at in this way. But overall, the amounts of data that you have to deal with call for machine learning because the data modalities are so rich. There's sequence data, there's imaging data, and actually each scale has associated measurements that you can take into account. If you remember this stack from molecular to organismal, each one of these scales has associated measurements that we can take and that we can correlate with health.
Yeah.
And that's where machine learning comes in, to characterize the phenotypes and to understand the mapping from interventions to outcomes.
Yeah, yeah. I think we're going to take one or two questions in the time that we pass the microphones around. I was curious, what is it like for machine learners to work with biologists and chemists, and vice versa? Do you guys like each other?
I mean,
is there on progress?
I always had this lab envy because I was never allowed to wear a white lab coat.
Yeah.
And my goal is that I integrate so well into the biologist community that one day maybe they give a white lab coat to me.
We'll get you one after
But
this.
it is a challenge, and you have to demonstrate that what you do is actually useful to them. And at the same time, you need to make sure that you don't just solve every individual's problem, because we know that building large platforms, foundation models, is the way to drive things forward. But then it's almost like the classical foundation model setup, where you have to think big and train those big models, but then you have to fine-tune and create benchmarks and downstream applications that are actually useful for the biological insight generation.